Okay, Gary, I'm going to start in a minute now. Okay, let's get started with this is lecture 5 of CSE 547, the discrete mathematics class. Last class we started, first of all, let's just start off. Are there any questions about any of the homeworks, any of the logistics, any of the anythings? Any technical or logistical questions? Okay, fair enough. Now, one question just to quickly ask. Some students, the TJ has not gotten too much traffic to his office hours, and I've not gotten too much traffic to my office hours. That could be because people already understand or already basically haven't needed to find us. The others were possibly not available. How many people have wanted to come to my office hours but couldn't make them because of their cards fixed with the class? I've got one person who's confessed to that. How many people have tried to tried to find the TA or at any point or TA's office hours? Okay, not much action yet. Again, these hours are on the web, okay, and I encourage you to look them up. If you need to see me and you can't, yes, question. Oh, Monday-Wednesday means Monday and Wednesday, not Monday too. So I have office hours on Monday and Wednesday. They have office hours on, I have office hours on Tuesday and Thursday. The TA has office hours on Monday and Wednesday, okay? And so together we've got every day, almost every day of the week covered. Any other questions, logistical or otherwise? Question? Okay, so the homework, just so you know, the homework ones are now graded, okay? They will be in the back of the room when you leave, okay? We've put we've almost put a copy of the solutions on the web, so you can take a look at them and see if you can make any sense of that. If you can't make sense of the solutions, you can come by and see me or the TA, okay? Any questions? Okay, what I would like to talk about now is go through a little bit more carefully, a little bit more deeply, just to make sure people understand the beauty of the proof that we did at the end of last class. I kind of rushed this a little bit at the end of last class, and I wanted to see that people just understand the combinatorial argument that we use carefully, and also maybe just to make sure we do the manipulations with the floors and ceilings right. Again, what did we talk about at the end of last class? I defined a BD sequence, which for a rational number, an irrational number alpha, was the sequence of numbers generated by the floor of alpha times I, for I goes from 1 to an infinite number. Okay? And what we showed was, or what we noticed was, if we build the BD sequence for a particular irrational number, like pi, which is 3.14 something or other, it'll basically be 3, 6, 9, 12, 15. It'll basically go every third number, except every once in a while it will skip. Okay, it will skip. So for example, here we have a skip from 21 to 25. That's a difference of 4. Okay? And that it generated numbers roughly every 3 numbers with an occasional skip. If we took the number pi over pi minus 1, which is also irrational, if pi is irrational, this is irrational. This is a number that's about 1.47. That, again, would go basically every other number or so, every number skipping maybe every other number. So it's 1, 2, 4, 5, skip 6, 7, 8, and so on. The interesting thing was the observation that these two sequences together describe exactly the integers. Every integer seems to be represented in exactly one of those sequences. Okay? And we showed that this was a property, this would not be a property of rational numbers, because if alpha was a rational number, we showed that there was a point, a number that would be generated in both sequences. Okay? Instead, this seems to be an amazing property of irrational numbers. Okay? And in fact, what we claimed was the following property. Okay? That if you have any two irrational numbers, 1 over alpha, such that alpha and beta, such that 1 over alpha plus 1 over beta equals 1. My claim was those sequences partitioned the integers exactly evenly. Okay? And what was the impact of this thing? Well, the fact that we had 1 over alpha plus 1 over beta equals 1, that meant that alpha had to be greater than 1, and beta had to be greater than 1. Okay, so these are two numbers that are irrational, that are both greater than 1, and if you solve for alpha in this equation, you're going to get something like the beta equals alpha over alpha plus 1 type of thing we had before, which is sort of where the, so the two pairs of numbers we have over here, this, if you take a look at it, was, I mean, if you look at what the relationship is, if you solve for beta in terms of alpha, you're going to end up getting alpha over alpha minus 1. Does anyone want me to do that, or do people sort of believe that? Okay. Anyone want me to do that? Okay, good. That's simple algebra. But what we'd like to now do is to prove that these two sequences partition the integers. Okay? And by partitioning the integers, we mean that no integer is going to appear in both sequences. Okay? And each integer will appear in exactly one of the sequences. Okay? That's what we mean by partition the numbers. We're going to use a counting argument to prove this. And counting arguments are kind of amazing things sometimes. Okay? You can prove some amazing things by counting them, showing that something has to exist because there's so many, there's a certain number of things. Okay? And, you know, on in the course, we're going to look at the probabilistic method in combinatorics a little bit, I believe. Okay? And there we're going to prove that things exist, physically do exist, discrete things exist, on the basis of a probability argument. Okay? Which is basically a counting idea. So here's sort of the first time we're going to see that kind of counting idea. What we're going to do is count the number of elements of each BD sequence less than or equal to a given n. So what was that going to be? N sub alpha n is going to be the number of elements in a BD sequence less than, defined by alpha, okay, which is less than n. So that was going to be, okay, the sum as k goes up to infinite, as k goes up, of the Iversonian, k times floor of k alpha is less than or equal to n. Okay? What did we do from here? Let's now count what this is doing. We want to know how many k's are there, how many different integer values are there, k, such that it starts at 1 and goes on, such that k, the floor of k times alpha is less than n. Well, we know that n is a, n is a integer. So if we say something is less than or equal to an integer, okay, we could represent that as being, the floor is an integer. If this is less than or equal to an integer, it's strictly less than that integer plus 1. This is a property, just to get more practice of working with the floors and ceilings. It has to do with one of the identities we showed last time. That if we had integer equality, clearly by adding 1 we had an inequality. If this was already less than that, adding 1 with it would keep it less. So that should be clearly true. Now that we have that this is strictly less than that, okay, the claim is we can drop the ceiling, drop the floor. Why? Because, well, let's think now, why could we actually just drop the floor here? Okay, again, I have to do these things again. Again, this is an integer. Okay, so if something is strictly less than an integer, okay, if this integer is strictly less than that integer, okay, dropping the floor is going to raise it up, but not up past the integer. So again, it should be clear that you can drop the floor. Okay? Now what we want to know is, by dividing both sides of the term by alpha, we want to know how many integers k are there that are greater than 1 and less than n plus 1 over alpha. Okay? That, I claim, is the number of elements of the BD sequence. Okay? Less than n. Okay? And this is sort of the special case of what we proved before. We have two open intervals, okay, we can count the number of integers in that interval. I claim it is given by this using the formula we had before. Okay? Any questions about what we've done so far? I claim this counts how many elements there are in this BD sequence. Okay? Likewise, by doing the same argument with just a different, where we replace alpha by alpha over alpha minus 1, this showed the number of elements in the first BD sequence less than n. This showed the number of elements in the BD sequence, the second BD sequence less than n. Okay? Now the key punchline, the place where we're using the combinatorial argument, okay, is that I claim that if we want to prove that the two sequences form a partition, it's enough to show that for all n, the number of elements in the left sequence plus the number of elements in the right sequence is exactly equal to n. Now, why is this? Okay? Let's say that I claim that people in this class, okay, some of you are smart, some of you are ugly. Okay? There is nobody who is both ugly and smart. Okay? Let's say that this is true. Let's say I line you guys up, okay, from 1 to n. Okay? And I keep, as you guys go by, I keep count of how many smart and ugly people I have seen so far. Okay? The first person comes by. I claim you can't be both smart and ugly. Okay? First person says, I'm smart. Okay? I've got one smart and ugly person. Second person says, I'm ugly. I've got a total of 2 smart and ugly people. Suppose, let's say, somebody says, I'm neither smart nor ugly. This is the third person that comes in. What is my situation? I now have a total of 2 smart people, 2 smart and ugly units. I have 3 people. Somebody had to not be both smart and ugly. Okay? But if, in fact, everybody is exactly one of those things, the total number of smart and uglies that I'm going to get, at any point I interrupt that sequence, is exactly going to be the number of people I've seen so far. Okay? If somebody is both smart and ugly, that would double my count. Then instead of I had seen n people, but I'd accumulated n plus 1 characteristics. Okay? And therefore my running total was not equal to n. If on the other hand someone was not smart and not ugly, I've now seen n people, but I only have n minus 1 units of smart and ugly. Okay? And that therefore means that this isn't true. If I can prove that the number of people, the numbers of numbers that are both smart, and the number of numbers that are ugly is always equal to the number of numbers, okay, then I've proven that no number can be smart and ugly, and every number is either smart or ugly. Okay? This is smart, this is ugly. Any questions about that? How many people understand the general line of the argument? Okay? Anybody confused by the general line of the argument? Okay? Okay? It's sort of it's a clever kind of an idea. We're going to prove that they're separate by basically counting. Okay? And so now I have to show that this formula is equal to that. Okay? So let's go and do that. Well, what is the sum of this term plus this term? Okay? My claim here is we've got n over alpha. Okay? This is an irrational, a rational over an irrational number. An integer over an irrational number is certainly not going to be an integer. Okay? So this is going to be a floating point thing. The ceiling minus 1 of a floating point thing is the same as the floor of that number. This is an identity we proved last time. Do we still believe it? Well, if this is a real number, the ceiling is going to raise it up 1 and then subtract 1 from it. That's going to knock it down 1. That's going to give us the floor. Okay, so that should be believable. Likewise, we do the same thing here. In order to now work with the floors, we're now going to use the identity that the actual interior is going to be equal to the floor plus the fractional part. So the fractional part is the real number, is the actual value minus the fractional part. We can write these things out. N plus 1 over alpha times n, plus n plus 1 times alpha minus 1 over alpha. Well, these are numbers out here. There's no reals, no floors, no nothings. We can just add them up. This is clearly going to be alpha over alpha times n plus 1. This is an integer. The next thing is, let's now add the two fractional parts together. If you believe that the two fractional parts, n plus 1 over alpha, the fractional part of that, plus the fractional part of n plus 1, alpha minus 1 over alpha, if you believe that sums to 1, then we're done. Because this 1 minus that 1 will give us the desired n. Okay? How many people, when they look at this, see that this is 1? Looking at this term, sort of look at that and say, yes, this is 1. How many people don't see that when they look at it? Okay, more people. Okay, I don't see it when I look at it. I can sort of see it, okay, because it's sort of going to be what? You've got some fractional part of this. It seems like these fractionals should add. It's alpha minus 1 plus that. This, though, I think needs a proof. Okay? So let's actually prove this identity being equal to 1 to give us more intuition about working with these things. First, I claim I'll prove it not for n plus 1, but for any integer x. Okay? So x is an integer. Alpha is an irrational number. My claim is the fractional part of x over alpha, okay, plus x over alpha minus 1 alpha, this is equal to 1. How do I prove this? I would convert the fractional part back to ceilings and floors, okay, and so I know that x over alpha minus the floor is the fractional part, same wise here. I can now add together the real parts together and get an x. That's good. And now what I'm left with is I've got x minus the floor of x over alpha minus x over alpha. Now, x is an integer. If you have an integer within a floor, you can take that out. Okay? You can pull that thing out. And so this is really going to be x minus x. And what I'm going to be left with is minus x over alpha minus the floor of x over alpha. Okay? Any questions? Now how are we going to work on it? This thing with the floor, minus inside the floor, is confusing. But we looked at some identities for that last time. Let's think how we deal with it. What is the floor of a number? By definition, the floor of the number is the greatest integer less than it. Right? So what is the floor of minus a negative number? Okay? Let's think about this again. Okay? The greatest integer less than it, okay? If you have a number x over alpha, is the greatest integer going to be, sorry, I always get confused when I do with these things. You can look up the identity, but let's try to work this thing out intuitively. The floor of the negative number, okay, I claim it's going to be, maybe we should draw this thing here. Sorry about that. Here we have, okay, let's say x over alpha minus x over alpha, okay. Which way is the floor going to be? The floor of it is going to be, by definition, the integer that is, what do you call it? That is smaller than it. I'm sorry about this. The integer that is smaller than it, okay, but the largest such integer. That I claim is going to be, actually, let's just think about what that's going to be. Okay. I want to claim that that is going to be the ceiling of x over alpha. Why is this? Okay. Let me just think about this for a quick second. X over alpha is this. The ceiling of x over alpha, if this was on a positive side of the number line, let's take a look. If this was x over alpha, on the positive side of the number line, this would be the ceiling of x over alpha. This would be the floor of x over alpha. Okay? So if we now sort of shift the line over here, okay, what we want is actually, I'm sorry, I'm getting fumbled here. Does anyone want to help me out while is this obvious to anyone? Okay, it's obvious to you. Okay, it's obvious. How do people vote that it's obvious? Okay, most people vote that it's obvious. So if it is obvious, then I claim that this is going to be equal to that. Now rearranging it, we have here that we've got the ceiling of x over alpha minus the floor of x over alpha. If this was an integer, this would be 0. But we know by definition that x over alpha is not going to be an integer because it's alpha is irrational. So what we do know is that that this is always going to be 1. Okay, and that's exactly what we claimed up here. Okay? Any questions about that? Okay, we've now proven that what we wanted to have happen happens. We have the cancellation here as we wanted. So lo and behold, the sum of these things is equal to n as promised. Any questions about that argument? One way or another. Question?
Yeah, I understand that this proof works for this case. But in general, how would you exclude the case where the number of elements exist in both sets equal to the number of elements does not exist in either sets, in which the n will still...
Okay, so what you're saying, what the question was, this is sort of shows in general that that we have some, I've shown that the sum of this is equal to n. Okay, the question of concern was maybe it's the case that you had somebody, two people in a row, one of whom was ugly and stupid, the other one was smart and ugly, and one was neither smart nor ugly. The total of 2 plus 0 is still going to be 2. The point is that this is going to, we've shown that this is true for all values of n. So I've proven this identity is true for every single value of n equals 1, 2, 3, to an infinite case. Suppose that what you were saying is true, that yes, at some value, okay, if I just proved this was true for n equals 56, that after 56 people had come along, the fact that I have 56, 23 ugly and 23 and 33 smart, 33 smart, that doesn't prove anything. It's the fact that I proved this not only for 56, but 1 through an infinite number. And so if there is going to be a skip, this formula, this inequality would not be true at that point of skip. The equality would break down at the first counterexample. It doesn't break down, and therefore there is no counterexample. Therefore it has to be true. That is the combinatorial argument. Okay? Good question. Any other questions? Okay? So it's a clever proof to see sort of the counting kind of an argument, and we'll see more of them over the course of the semester. Any questions? Okay. What I'd like to now do is look a little bit more at some other situations where ceiling and floors will come up. One place where they will come up often is in recurrence relations. Okay, when you're trying to analyze a a divide and conquer algorithm, okay, it's often the case that you're dividing the space of possible answers, okay, n into two different possible into two pieces. Whether or not depends upon the value of n, whether or not it's possible to divide it into equal pieces. So let's think of two of the algorithms for divide and conquer that you're familiar with. In a merge sort, you take the keys and divide them equally, sort them, and then merge them. Okay? So but the only circumstance under which you can always take a merge sort and recursively divide it so that both sides become evenly is when n is equal to 2 to the k. When you've got a perfect power of 2, then you start out, at the end you have one element. Before that you merge it at 2, 4, 8, 16. Okay? Similarly in binary search, what do you do in a binary search? You check the middle key, okay? And then break the problem into, if it's not the same as the key in the middle, you look to the left or you look to the right, for it to be a perfectly even split, what you need to know is that the amount that's going to be on this side is always going to be the same as the amount on that side. An even split in merge sort happens when you've got an even number. An even split in a binary search happens when you have an odd number. And to perpetually get the case that we always look at, the perfect case, it really needs to be the case that for binary search you need to have a power of 2 minus 1. Okay? So if you have n equal to these things, those algorithms, the analysis works out without ceilings and floors. But in general, you don't get a perfect decomposition. Okay? In general, we make use of the following identity, which, okay, should be pretty clear, that n is going to be equal to the ceiling of n over 2 plus the floor of n over 2. Okay? This is the bigger half. This is the smaller half. Or in the case that n is even, it breaks it down identically. Both halves are the same. Okay, because if n is even, the floor is equal to the ceiling. So if you look at the correct merge sort recurrence, okay, what you really end up getting usually is f sub n is going to be equal to, if f sub n is the number of comparisons in merge sort, okay, it's f of the ceiling of n over 2 plus f of the floor of n over 2 plus n just one comparisons to actually merge the two lists. Okay? Now usually when you see it written in a textbook, the solution for merge sort recurrence, what do you usually see? Does anyone remember what the usual recurrence you see in a textbook? Okay? It would be something that says that the number of comparisons you need to merge merge sort n elements is 2 times f of n over 2, combining these two terms together plus n minus 1 or order n. It's much easier to deal with these recurrences if you drop the ceilings and the floors, okay, because then you can combine these two pieces together, okay? And in general, okay, it doesn't really change the answer. Asymptotically, it won't change the answer, okay? So if I'm dealing with a recurrence, to be honest with you, usually the easiest thing to do is to just drop the ceilings and floors and get a rough answer, or claim your answer holds exactly for the specific case where the divides always work out right. Okay? That, in fact, in all my years as an algorithm analyst, is something that that's always been good enough for me. Okay? Sometimes, however, you can get a better, more analysis of a recurrence by being more careful. Okay? And I'd like to show you one example of that now. Any questions? Okay? So let's look at a sequence of numbers, which they describe in the book, which we'll call the Knuth numbers. Okay? They're given by the recurrence relation. K sub 0 is equal to 1. K sub n plus 1 is going to be 1 plus the minimum of the floor, the Knuth number of the floor of n over 2 times 2, and the Knuth number of 3 times the number of the floor of n over 3. Okay? This is a sort of ugly-looking recurrence for a couple of reasons. Okay? First of all, you've got a min in there, which makes it look like it's harder to deal with. Then you've got these floors in here. Is it possible to drop the floors and get a rough idea of what's happening? Okay? In this particular function. I proposed last time it was easy to just drop the floors to get an idea of what's going on. Could you, with this recurrence, get an idea of what's going on by dropping the floor function? The floor. And I claim the answer is not really, because these are actually indices to a number. It's not like it's a function. The Knuth number of n over 2 is not defined. Okay? So you can't really deal with that. Let's look at what the function actually looks like. I claim these are the first few terms. Let's work through it. Okay, for k equals 7, for k equals 5, n equals 5, assuming you believe my smaller values, let's just make sure we get this thing right. For n equals 5, what is it going to be? It's going to be 1 plus the smaller of 2 times What's the floor of 5 over 2? 2. So it would be 3. It could be 1 plus 2 times 3, which would be 7. Or it could be the floor of 5 over 3. Actually, what is that? What is 5 over 3? Okay, the floor of 5 over 3 is 1. If we go back to 1, Knuth number of 1 is 3. 3 times 3 is 9 plus 1, that's 10, that's good. But, unfortunately, we want the minimum. So the earlier value of 7 is what worked. Okay? Any question? Okay? So, I claim if you work this thing out, you get an erratic-looking sequence of numbers that doesn't seem to have any particular insight whatsoever. Okay? Questions? Well, what I propose that we do is, since we can't actually getting a closed form for these seems tricky, let's prove a bound on it. I claim that the nth Knuth number is always greater than or equal to n plus 1. Why do I believe it? 0 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, sure enough, all of these things are greater than n plus 1. Okay, so potentially that seems like a thing to prove. Let's prove it by induction. How do you do it by induction? Well, by induction, if we assume that, that the value of kn is greater than or equal to n plus 1, my claim is k plus 1, by definition, is going to be greater than or equal to, okay, 1 plus the min of, if I replace this, if kn is greater than this thing, if I replace this by the value I have, the real answer can only be larger than that. That's why I'm justified in saying that this is greater than or equal to that. So let me replace this thing by what I know. I know that if floor of n over 1 is here, the Knuth I'm saying is greater than n over 2, the floor of n over 2 plus 1. This is going to be n over 2 plus 1, the floor of n over 3 plus 1. I want to know what is the min of this. Okay, this was 2 times that. The 2 times 1 is going to give me a 2 here. The 3 times 1 is going to give me a 3 here. How can I now deal with an expression? What is the minimum of 2 floor n over 2 plus 1 floor 3 n over 3 plus 1? How can we think about what the minimum here is? Here, let's do some kind of a case analysis to think about it. My claim is that by definition, floor of k times n over k, we can rewrite n as being of the form m times k plus r. Why? K is going to be, we can always write n, if we divide it by k, okay, the remainder we get is r. The full integer is going to be k. M times k, we can always break any integer down to be the integer quotient times n, times, okay, if we divide it by k, we get the integer quotient plus the remainder. What is the floor of mk plus r over k? This we could break down. This is going to be an integer, m. We could pull that out, okay? What's the remainder of that number divided by k? Okay, the floor of that. What is that going to be? 0. Why 0? The remainder, by definition, had to be less than or equal to k. Had to be less than k, not less than or equal to. Less than k. So what we know is, in fact, that this is going to be k times the, the integer divisor, which is really going to be the same as n minus the remainder. Okay? So let's think about what's actually happening now. Here we have something that for any n, we could write these two as n minus the remainder. Okay? Correct? Now let's do a case analysis. Think about when is n minus the remainder minimized. My claim is that n minus the remainder is minimized when the remainder is maximized. Correct? The remainder is maximized when it is k minus 1. So I claim that the worst case that we can get here, okay, is going to be when this is n minus k minus 1, okay, k being 2, 1 being 1, okay, plus 2. Here we have the remainder when we divide it by here. Here k is 3. So here we have n minus sort of 2 minus 1, 3 minus 1, or 2. Can I raise the slide? Good question. Okay. So here what I'm saying is, we've proven that this term is going to be n minus the remainder of n. We want to minimize that thing. Okay. The smallest it could possibly be is when the remainder is very, very bad. Okay, the worst remainder we could get is k plus 1. Okay, substituting that in here, okay, lets us see that in fact both sides of this thing work out to be n plus 1. Okay, the min of n plus 1 and n plus 1 is n plus 1. 1 plus the min of that is going to be n plus 2. So my claim is that this actually suffices to show what we wanted. We've shown that for the Knuth number n plus 1, the n plus first Knuth number, is in fact greater than or equal to n plus 2, if, in fact, in general, the nth Knuth number is greater than or equal to n plus 1. Okay? The interesting part of the analysis is over in here, where we sort of did it, we sort of thought about, we wanted to figure out, prove a bound on it. We thought about what was the worst case of this. Okay? And defined the worst case in terms of something else, namely in terms of the remainder. Okay? And then showed how to deal with that. Any questions about this analysis? Okay? Again, the Florence tend to be ugly things. Okay? And so you can't get around with them with this classic tricks of algebra. You have to finesse them and deal with special cases. Any questions? Okay. I'd like to show you one more amazing thing about that happens when you start thinking about ceilings and floors and fractional parts. Okay? Which is the BD sequence thing that I showed you before, where you partition the integers, and you can sort of partition the integers among these two sequences, was amazing. Here's another sort of surprising result based on fractional parts. This actually isn't really in the textbook, I think, but it's still an amazing thing. Okay? Suppose, let's say, that we have an irrational number, alpha, and we consider the sequence of the fractional parts. Remember, the BD sequence was alpha I minus the fractional parts. It was the floors. Let's consider what are the fractional parts of alpha times I for some irrational number I. Okay? What is the smallest value alpha times I could take on? Okay? For the fractional part of alpha times I. What's the smallest value it could take on? Okay? 0. What's the largest value it could take on? Okay? If it's a fractional part, it could be 9999, anything less than 1, right? In fact, I claim if it was an irrational number, it couldn't take on the value of 0. Okay? Because then we would have if it really took on the value of 0, then I times that, it would have been a rational number. Okay? So we've got a sequence of numbers that are between 0 and 1. Correct? Let's think what happens if we go and insert these numbers in sequences into a number line. Okay, here I have a particular sequence of numbers. Let's say my number alpha was pi. If I started to insert them, my first insertion would happen here at like 1.14159. I would have broken my line into two pieces, one small and one large. The next point I insert is going to be another multiple of that fractional part away. I would now have the line broken into 3 parts, but only 2 distinct distances. Correct? Because the distance from here to here would be the same as from there to there. Does everyone agree with that? Okay. If I consider just sort of, 0.14159 times 1 and 0.14159 times 2, the distance from here to here is 1 times that fractional part, This is 2 times that fractional part. 2 minus 1 gives me that fractional part again. So this distance has to be the same as that distance. Okay? How many people see what I mean by that? How many people are confused by this? Okay? So I claim that we can go and insert these numbers. If you think about it, what's going to happen here is, up until the point where we wrap around, when we consider the first 1, 2, 3, 4, 5, 6, 7 insertions, I claim the distances between neighboring points on that line are going to, all these distances are going to be the same. The last one is going to be different. So that defines a total of 2 distances on the line. Okay? Everybody agree? Now, what happens when we add the next value of alpha to it? It's now going to wrap around and define another point here. Okay? And we're now going to go come up with other distances defined. Now if you look at this thing, there's the distances there. There's distance between the blue and the green and the red and the green, and so on. Okay? What's interesting is if you go through this exercise, you will see that no matter how many points you insert, there are only 3 different distances defined between neighboring points. Okay? If you've put in n points on this line, that's going to break the line into n plus 1 pieces, correct? Because you're going to have a region before the first point and a region after the last point. Potentially, you would think if I take n points and scatter them on a line, they might define n plus 1 distinct distance integer values or distinct distance values. The interesting thing is that no matter what n you use, and no matter what irrational number you use, there's only going to be at most 3 different distances defined between pairs of points, between neighboring pairs of points. Okay? Any questions about this? Okay? About what this is or is not? Okay, question?
So if you did that again?
If I now do this again, what am I claiming? I now add another point. It's going to go maybe here. Okay? I claim there will still be a total of only 3 different distances. I stick another one in here. There'll be only 3 different distances. 3, 3, 3, 3, 3, 3. At most 3 distances. No matter how many points I insert. Okay? No matter how many times I wrap around. No matter if I stop in the middle of wrapping around. I claim there will be only 3 such distances. Okay? Which is kind of surprising. Okay? Let me show you another. Okay, any questions about that? Okay? Again, it's sort of funny because rational numbers I think of as irrational. Okay? There's not much you can do about them. Okay? Yet here we've got a very, very discrete property coming out of the irrational numbers. Okay? Namely that there are only 3 such distances you can define. Any questions? Let me show you an example of why this might be true. The proof of this whole property is actually kind of complicated. But I'd like to show you why you might believe in it. So this is an example I drew up yesterday to try to help me understand this a little bit better. Okay? And hopefully you can see it on the screen. If not, we'll ask, or if anything's fuzzy, we can ask about it. Let's now plot out a timeline of what distances get created when we consider multiples of some irrational number. We'll call it theta here. Okay? So the first point I'm going to insert, this is going to be my line from 0 to 1. Okay, so if you want to take a look at it, this is going to be, does anybody have a pen I can borrow quickly? I mean, this is what I say. So this may be more delicate than a magic marker job. Here we've got 0. Here we've got 1. The first number we put down, if the fractional part is theta, is going to be here. Correct? Is the first point we inserted. That's what I have the 1 there for. I claim that that will have broken the line into 2 distances, theta and 1 minus theta, which I'm going to define as x. Okay? let's say that the next one we insert, let's say theta is greater than n over 2, than 1/2. So the second thing we insert wraps around to go here. Okay? Now I've got my first point here, my second inserted point here. How many distances, how many intervals are defined by those 2 points on the line? 3. How many distinct distances are defined? Not 3, but 2. Let's look at that. What do we actually know? Here we've got that 1 is equal to theta plus x. Let's call this other distance, the distance where the third point sits from the left, let's call that y. Okay? Now what are the distances that we get here? Well, we've got here, the distances that we've got here are, this is going to be the distance y. This is going to be the distance theta minus y. Correct? Because it's going to be between these 2 points. Does everybody agree that this distance here is going to be theta minus y by definition? And this is going to be x. Well, let's now look at the analysis of that. Okay, what do I know? That at the point before I've wrapped around for the first time, I've used a total of k1 instances of theta. In this case, k1 is 1. Okay? And what I've got is that k1 times theta plus x equals 1. Why? Because basically the furthest position of the furthest point plus x is equal to 1. By definition, k1 times 1, maybe I'll zoom this thing up against my better judgment. k1 times 1 theta is going to be what it took to wrap around one time before more. Okay? And if you do that, what do we get? The total distance here is going to be 1 plus y after we've used k plus 1 things. Correct? So lo and behold, what do we know? We know that k1 theta plus x equals 1. k1 plus 1 times theta is equal to 1 plus y. Together that implies that y equals theta minus x. Okay? If y is equal to theta minus x, then this thing has to be x. Okay? And so the distances we have so far are y, x, and x. Okay? Only 2 distinct distances defined. Okay? So everybody see that in fact we do not have 3 distinct distances, but only 2 of them. Okay? What happens if we go the next time around? Okay? In this particular example, okay, I'll claim the next one wraps around further. I did this with a ruler. Adding another theta to this, my third point is a distance, let's say z, from the left end point. What are the distances now defined? Well, I've got z, I've got y minus z, I've got x, and I've got x. Okay? What do I actually know? By definition, okay, let's just think about this thing here. 2, the second interval here, 2, this plus this, is going to be equal to, okay, let's just go back to here. If I go back to the last one before this, here, I'm going to say that 2 is going to be equal to k1 times theta, in this case theta is 2, k1 is 2, plus 2x. By definition, 2 is going to be equal to the number of revolutions around so far times theta plus 2x, because that was the remainder. Likewise, if I add one more revolution, I've got that I'm going to have 2 plus z, okay, z being that remainder. Combining these two, this tells me that z is going to be equal to theta minus 2x. Okay? And going back to the diagram now, okay, What we now know is that theta, that z is equal to, that z is equal to theta minus 2x. What does that tell me? Well, if this was x, if theta x, that theta was equal to y plus this thing, my claim is that if we've proven that theta is equal to z plus 2x, theta, z, 2x, lo and behold, that means that this interval also has to be an x. And lo and behold, the distances that we've created are z, x, x. Okay? Right now, actually, what we created was z, x, x, x. Okay? And still only created two distances. Inserting another point, I don't want to go through the geometry again. But what I am showing you is that, in fact, a lot of these distances coincide. Okay? And that, in fact, if you keep going around on it, you will see that the next time we insert something, it divides a previously biggest thing in a way that one of the two distances it gives me so far is the same as a distance I already had. If when I take a interval and I divide it into two distances, neither of which I had, that would increase my number of distances by 2, which is potentially dangerous. Okay? In general, I'm going to keep it constant because one of these two pieces is the same as a distance I already had. Any questions about that? Okay? It's kind of an amazing property, especially because if you take a look at where at the end, again, after I'd inserted 4 points here, the order of my sizes were z, x, x, z, w. The order of these pieces is not sort of nested 1, 2, 3, 1, 2, 3, 1, 2, 3, but seemingly some weird function generated by the fact that this was an irrational number. Okay? But again, lo and behold, only 3 distances suffice. Any questions about that? Okay, it's kind of an amazing property. Why is it interesting or why is it useful? It turns out that this is actually a property that comes up and is used in the analysis of hashing algorithms. Okay, what is hashing? Okay, hashing is a computer science information retrieval idea. Okay, that's fairly important, which is that you take let's say you want to build a data structure to store keys, let's say people's names. Let's say you want to build a data structure to store numbers from 1 to m. What you could do is build an array of 1 to n, where n is smaller than the range of possible keys. Okay, take each number that you want, multiply it by a constant. Okay, to give you a big number, and then take the remainder of that mod m and to give you the position in your index array where it will sit. For hashing to work out well, what you need to do is to have it mix up keys in a way that if you have a set of keys that are fairly close together, so that in real data sets it's often the case that you've got lots of numbers that are, let's say, fairly close to each other. Let's say that we were going to store up salaries, okay, and we have we want to hash on salaries. Here we have a bunch of graduate students in this room, all of whom are earning almost the same salary, okay. One guy may earn $100 a week, one may earn $101 a week, okay. There's not going to be a big difference here. For hashing to be a useful scheme, we need to know that when we insert a sequence of numbers that are very close to each other, that they get spread far apart in the hash table. What does this 3-distance theorem tell me about what happens? If I have numbers that I'm putting in my hash table, numbers I plus 1, I plus 2, I plus 3, that a long run of consecutive numbers. If I have a bunch of numbers stuck in a line, spread as far apart as they could be, they would define only one distance between them, right? If I give you a bunch of points on a line, suppose I give you, want you to put down 5 points on a line, spread them out as far as possible, what would you end up having? you would end up having it such that each one of these distances was equal to 1/6, correct? What this three distances theorem says is that, in fact, any irrational number you use does a very good job of spreading the keys out evenly, okay? Because, in fact, instead of there being one distance defined, it has to do a pretty good job spreading it around because there's at most three distances defined, okay? And this is one of the justifications for using this kind of a hash function, okay, as that is done. Any questions? Okay. And I think it's an amazing theorem and an interesting thing. And again, the motivation is to hashing. Okay. Any questions? Okay. The place where we're going to end up using sort of the ideas of floors and ceilings, probably more than anything else in this course, is going to be when we start talking about mods. Okay, thinking of in terms of remainders and the quotients. Okay, as we've shown before, okay, the floor function provides a natural way to define the quotient and the remainder. If we have two integers, n and q, okay, we wanted to talk about n and m, and we want to talk about what happens when we divide n by m. Okay, the quotient is, the integer quotient is the floor of n over m, and the remainder is n minus m times the quotient. Okay? Convince yourself of this. This is sort of fairly straightforward definition. Okay? That the remainder is by definition going to be, the remainder of n divided by m is going to be m minus m times the floor of n over m. Okay? How many people believe that, can see that and see that it's clearly defined correctly? Any uncertainty about that? Okay? So this is the function that you've probably used on a calculator, in a computer programming language or whatnot. The remainder function proves to be useful enough that we define a function we call the mod function to return what the remainder is. Okay? And so by definition, x mod y is defined as being y minus x minus y times the floor of x over y. Okay? Any questions? Now, this mod function, thinking about x minus y, x mod y as the remainder, makes it pretty easy to calculate. All of you have done division, and you all know about remainder. So the remainder of 5 mod y divided by 3 is clearly 2. And again, that's 5 minus 3 times the floor of that. The quotient is 1, so 5 minus 3 is 2. In fact, this definition gives us a way to compute what the remainder, what should be returned by the mod function when you've got positive and negative numbers. Okay? If you accept this is the definition of mod, this is what I claim 5 mod minus 3 is. Okay? What is the floor of 5 over minus 3? Okay? That's 5 over 3 is going to be like 1.6. The greatest integer less than that is going to be minus 2. 3 times minus 2 plus 5 is minus 1. Okay? Minus 5 mod 3 is going to be different. Okay? Because, okay, so here we've got the same quotient, the floor here. So this is going to be minus 2. Minus 2 times 3, before we had minus 3, so it got rid of that. Minus 2 times 3 is going, minus 2 times 3 is going to be minus 6. Minus 6 is plus 6. We get 1. Okay, minus 5 minus mod this. Again, we now have the floor of this, which is going to be 1. 3 times 1, minus 5 times that, minus 2. Okay? So what's interesting to note here is, again, I find it difficult to keep these things straight, okay, without going back to the definition. And in fact, my understanding is a lot of different implementations of programming languages use very inconsistent definitions of what mods of negative numbers are. Okay? So this is what we're going to use throughout here. Okay? Any questions? Okay? It's a natural definition. Now, we're going to see the mod function in several guises throughout the semester. One interesting property of it is that it obeys the distributive law, okay, which is something that we didn't have for just sort of floors. What the distributive law means is that C times x mod y is Cx mod Cy. Okay, this means basically that if we have the same thing on both sides of the mod, this means that we can factor it out. Okay? Does this seem obvious to you? Take a look at that. Okay, does this expression seem obvious? Okay? That C times the remainder of this is the same as Cx, the remainder of Cx divided by Cy. To me, this isn't completely obvious. Okay? So let's look at a proof of it. How would we prove this thing? C times x mod y. Well, what is x mod y? By definition, it's x minus y times the floor of x over y. Okay? C times this, we can certainly multiply this out. Okay? It's Cx minus Cy times that. Okay? Within the floor, we can't sort of just move in the C, okay, and take the C and multiply that thing out. But what we can do is write this thing as Cx, is multiply the fraction inside here by C over C. That doesn't actually change the value of this thing. Correct? It's like multiplying it by 1. But what's interesting about it now is now we could now rewrite, instead of having x, we have Cx. Instead of having y, we have Cy. Instead of x, we have Cx. Instead of y, we have Cy. This, by definition, is Cx mod Cy. Okay? By simply just reusing our definition of what the mod function is. Okay? And lo and behold, the mod function obeys the distributive law. Okay? Any questions about that? Okay? So a special case that's of interesting is what if C is equal to minus 1? Okay, my claim is that that minus 1 is equal to, that this would be minus 1 times this is equal to that. We could multiply both sides by the minus 1 to get rid of it here and put it there. X mod y is minus x mod minus y. Okay, for trivia thing. We're going to see the next several lectures are going to be on number theory. And we're going to talk about congruences, and we're going to talk about divisibility things. And in fact, we're going to be using the fact that sort of modular arithmetic obeys the distributive law, okay, later on. Any questions? I'd like to show one final identity concerning floors and ceilings, okay? And this has to do with the problem of arranging sort of items into columns when things don't exactly work out. Okay? If I have n items, and I put them in m columns, if n is a multiple of m, then in fact we perfectly fill up the matrix. So then we would have you know, the quotient of m over n columns, of which would have the remainder. Oh, wait. Okay. If in fact n was equal to k times m, we could arrange them in k columns of m or m columns of k. Okay, and that would be fine. In general, you often want to arrange things in columns which aren't, you know, when they aren't necessarily perfect multiples. One example of this that I think many of you are familiar with is when you list a directory. In Unix, for example. There you've got a situation where to make it easy to read, they put things in columns. Okay? And the question is, and they can't guarantee that they fill columns. So where do you leave the extra spaces? Okay? One possibility would be, since if you want to leave the things in sorted order, you want to count down and be able to scan down a column like this. One possibility is you list them in order like this. Fill out, you find okay. You know that if you're going to, you find out what's the smallest number of elements you need in a column, a full column, in order to make sure that you can specify it in that many columns. Fill full columns until you get to the last one, and just put as many as you need, the remainder, in that last column. If you do that, the last column can be quite lopsided. Okay? And it's actually how ls works in Unix. I actually did it today and check. In fact, you can end up with fairly ugly looking things if in fact you have, let's say, 4 columns, each of which are fairly long. The last column might only have one thing in it. Okay? If it just sort of works out that way. If the number of elements you're putting in are 3 times some long number, plus 1. So you only have 1 element in the remainder. The question is, what shape do you do? What algorithm should you use in order to fill up the column as it is? Okay? If you want to, instead of having all the remainder stuck in the last column, you would like to have the last row be only partially full. The following sort of algorithm would be sufficient to do it. Find out how many rows you have. Fill in as many as there are rows up until the last row. But that doesn't really help you very much. Because if you're listing the file names as you do in Unix, you want the elements in the first set to be the numbers from 1 to, basically you want the numbers to be sorted like this and not like this. So the question is, in this kind of an arrangement, how many elements are there? If you want to make it so that every column contains within 1 of each number of elements as in here, how many elements should be in each column? Okay? My claim is the following analysis will do that. Any questions about what I'm trying to do or why? Why may be a good question, but okay. But let's just look at it because it's kind of an interesting identity that we're going to get out of this thing. My first claim is that n, the number of elements, is going to be the following. Can always be written as, by using the remainder idea, this is the remainder, this is the integer quotient, okay? N divided by m, n can always be written as m times floor of n over m plus the remainder, okay? So one way to think about this is, if you want to think about n items and m columns, one way you could think of it as is the smallest column is going to have the floor of n over m elements in it. Okay? The biggest column is going to have one more item. Okay? If we want to make the columns as equal length as possible, they're only going to differ by one, they only need to differ by one number. Okay? And so I claim a way to think about it is, if we have n being written as the remainder and the integer quotient, this could be thinking of, we have, for each element of the remainder, that's going to be adding 1 to that many columns. Okay? And so one way to think about it is that we have n mod m columns of the floor of n over m plus 1. Those are the big ones. And m minus the remainder, all the rest of the columns have 1 less. Okay? Any questions? Okay? And as I say here, that so long as there is some kind of remainder, okay? So unless the thing divides perfectly, okay, there is going to be at least one column that is going to have one more element, okay? If these things don't divide evenly, floor of n over m plus 1 is the ceiling. And this gives us another way to write that thing. So it could be said that we have the ceiling of n over m for the remainder's worth of columns, the floor otherwise. Any questions? Well, what's interesting is this now suggests an algorithm to figure out which elements go in which column. Okay, and we're going to use this algorithm actually to prove a kind of interesting identity. Okay? The first column, by definition, contains n over m elements, ceiling of n over m elements. Okay? Once we have that done, the remaining number of elements we have is the total number of elements minus what we've subtracted, minus what we put in the first column, and m minus 1 columns from that. Okay? So what we can do now, I claim, is that this is a way to sort of reduce this to a recursive problem. Okay? How many elements will there be in the kth column? Well, if you think about it, we've agreed that, going back to here, that in n mod m columns, there's going to be the ceiling of n over m. In the rest of the columns, there's going to be the floor of n over m. Let's think of a function that has this property, that for k between 1 and n mod m, we get the ceiling of n over m, and for larger values of k, we get the floor. My claim is this function does the job. The ceiling of n minus k plus 1. Okay, let's look at what happens. If k is going to be less than the remainder, okay, n minus m, okay, if subtracting out less than the remainder, the ceiling is going to be higher. Once we subtract out something more than the remainder, then in fact that's when this number is going to go down. Okay? Look at this for a second, just convince yourself of this. If we take a look at this thing, this can be written as the integer part plus this fractional part that's either going to go up, plus the. Okay, if we think about subtracting by k, under what condition, if we take this thing and we keep enlarging k, how much do we subtract till it goes down? Well, the transition point will be when we subtracted off all the remainder. Okay? Because then, once we subtracted off the remainder, then subtracting off another one will drop. We would then have an integer value. Subtracting off another one will drop the value of the. Will change the value of the ceiling. Okay. My claim is that this function encapsulates the constraints that we want. Okay. And if you believe that, we get a kind of interesting identity. That n is going to be. This is a sequence of numbers defined for the entire. For every column, this is going to be the number of elements in the first column, second column, third column. Okay? This is given by this counting value. I claim we get a kind of interesting identity because this is going to be one more than this for all the terms until we get below the divisor. Okay? Any questions about that? Okay? I urge you to just go through and convince yourself with the indices that that's right. Okay? And we'll leave it at that. Any questions? Okay, let's leave it at this. Okay, next class we're going to start talking about number theory in a more serious way. I think there we'll get to some maybe more interesting and more powerful things. Okay, thanks for your attention. I'll talk to you then.